Save, close, PowerPoint, chapter 2. Booyah. Here we go. All right. So all right, now motion along a straight line. So various things we're going to be looking at throughout the chapter, of course, is the idea of displacement. Man, do we struggle with this sometimes. And it's simple, but we get a little confused with the understanding of displacement. We're going to look at something called instantaneous velocity, average acceleration, and instantaneous acceleration, freely falling bodies, and then how to look at and analyze acceleration that is not constant. Not all acceleration is constant. Kinematics. So, and yes, there's some terminology. And yes, you need to know what it is. Okay, or I wouldn't have it up here and wouldn't be going over it. Is the study of motion. And that's a very basic definition, but it is very precise. We are looking at motion. So my mouth is moving, so we are studying kinematics. Okay. That wasn't funny. Okay. All right. Every time we move, it's kinematics. Anything that's moving is considered, and you study it, it's considered a study of kinematics, okay? We get into dynamics, which is also a study of motion, but it's a little bit more involved, okay? And we'll talk about that later, okay? Now, velocity and acceleration, of course, are important terms to understand. We're going to define velocity and define acceleration. But first, I want to define displacement. What is displacement? All right, now, we need to try to get a basic understanding of displacement. Displacement, before we do velocity, is the change in position with respect to direction. Okay? What is distance? Distance is not the same thing as displacement. Distance is basically the length between 2 points. How far is it from point A to point B? No direction involved.
Is distance a straight line?
Doesn't have to be. Doesn't have to be. Okay. I mean, I can walk 3 meters this way, and then turn at an angle and walk 3 meters this way, and then 3 meters this way. Okay. Distance is the distance between 2 points. So, yeah, in a sense, it would be a straight line. Yeah, because from there to there, there to there, and then there over here. So, yeah, in a sense, it would be. In other words, what I'm trying to get at is what you're saying is how we measure it, but I don't have to walk a straight line. I can walk crooked, but I'm going to measure to the point everywhere I made a turn. Whereas displacement is the change in position with respect to direction. In other words, that's going to be, I can do this right here. Okay. Then I want to measure my displacement from here to where I stopped. Never mind all the snaky stuff.
So displacement from start to end?
Yes. But it's with respect to direction. You got to throw in a direction. Okay. And how do we determine displacement? Mathematically, displacement is delta x is equal to x final minus x initial. Delta x is change, boy, you better get this now, in displacement. Okay? It's change in displacement. And notice it's final minus initial. Okay. Insert, home, new slide. All right, so let's look at this. So, oops. Why is it doing that? Why in the heck did it jump? What has happened to my slideshow? Oh, good grief. End show. There we go. Now. Okay. So, all right, now. So the change in displacement, delta x is final minus initial. So, let's graph it. Okay. If I walk 5 meters, 10 meters, okay, and then I turn around and I go back let's see, let me make sure I do this right. All right, hang on a minute. I want to make sure I say this right. Okay. Let's do straight line. All right, I walk out from point 0, 5 meters. I'm going to keep it simple. There's 0. And then I turn around and go back in this direction 3 meters. That's 5. Oh, that's 5. And this is 3. All right. What is my displacement? What is my change in displacement? Okay. Okay. I have a change in displacement. Now notice, now, my final was 3. My initial was what? 5. So, my change is what? Now, does that make sense? Well, did I turn around and come back? I was traveling east. There's my direction. Now I turned around and go west. Okay. So I have a change in displacement of what? -2. Okay. So that's how much change in displacement there was. But how much total distance is there? What's the total distance? Total distance is 8 meters. Okay? So we've got to be really careful. We've got to be really careful when we say, well, I walked 5 meters east and then turned around and went back 3 meters west. We changed direction there. Okay? We changed direction. Okay? And so we've got to be aware that when there's a change in direction, we change our displacement. Okay? Okay? So we've got to be really careful. Okay? Okay. Now, all right. Okay? So if I walk 5 meters, stop, turn around and come back 3 meters, I've only displaced myself what? 2 meters, but I'm headed back the other way. Because from the original starting point, I was at 0. Okay? So displacement, you've got to look at direction. Okay? My change in displacement, I didn't say total displacement. My total displacement, of course, would still be 8 meters. But my change in displacement was 2. Because I started at 0, I went out 5, came back 3, so I've only displaced myself from the original starting point 2 meters. Okay? All right. So we've got to be really careful that we understand that displacement is not the same thing as total distance. Okay? For example, if you do an average speed calculation going to the beach, all right, I'm going to the beach, and it takes me 6 hours to get there, and it's 350 miles. Okay. Well, 350 divided by 6, bam, what is that? You ran about, what, 35, 6 divided by 35, almost 60 miles an hour. Let's say it was 360 miles. 6 are going, yeah, so it'd be 60 miles an hour was your average speed, okay? But now that doesn't say anything about stopping. See? And you might have been doing 80, you know, but you stopped for an hour, okay? So see, you got to understand there's a difference in average speed and average velocity. And that's where the difference in the two comes in. All right, so let's look at a little bit more in-depth definition of those two. Okay, I want to make sure you understand. Whoa, okay. Okay, now. All right, so average velocity, and here's another formula now. Average velocity is the change in position. The change in position. Okay? So we have x2 minus x1 over t2 minus t1. Now typically our time change is going to be very straightforward, but we could start at 1 second. We could start the clock and say, okay, 0, 1, go. So we don't always start at 0, but sometimes we do. So we have the change in position over the change in time. Okay? Okay. All right. And notice it says final x coordinate. That's on the x-axis, right? Final x coordinate. See, that makes it a whole different ball game. Okay? All right. So we have an equation of what? The average velocity is equal to the change in displacement, that's displacement, over change in time. Okay? Now, again, notice how they have annotated all these. It's right here. It's on the PowerPoint, so I don't need to rewrite what they've already written. I wrote the formula, okay, but that's important. And this is called what? Average velocity. All right? And it does reference direction. And where does my direction come in? Coordinate. Coordinate. All right, let's move on. All right. Okay. Now this is a really good rules for the sign of x velocity. This is really good. If x coordinate is positive and increasing, it's getting more positive. Well, duh. All right. So what does that mean velocity's doing? Positive, particle is moving in positive x direction. What do you mean? Let's draw it. Watch. Now, I hope I'm making sense. Now, I know some of this is new for some of you. All right, watch. So if it's increasing and it's positive and increasing, that's positive x, y'all, then my particle is moving in what? Well, it's got to be moving in the positive x direction. I mean, it's physically impossible to be going positive x, increasing, and have a negative velocity. Unless you're in another dimension. And you're Einstein. Okay. Positive and decreasing, then that means what? Then the particle is doing what? Could very well be slowing down or going in the x direction. Negative x direction, excuse me. In other words, if it's decreasing, it's positive, but it's decreasing, getting less positive, then that means it could be doing what? So what are you saying, Mr. Shields? Now, see, this is where we get a little in our mind, okay? You mean I can be over here in the positive, I could still be over here in the positive x-axis, but yet be a negative velocity. Yeah. What you could be doing is you could go out so far, but then be slowing down and turn around and coming back. But you're still over here in the positive x, except you've changed directions. Does that make sense? That's what they mean by that. Okay? That's what they mean by that. I want to make sure I explain this, okay? I hope I'm making sense, okay? So I know that you think, well, how can it be positive and negative and it's a positive quadrant? Well, you've changed direction, okay? And see, direction is everything. Everything with velocity and acceleration. Oh, man, you got to get that. Direction is, you can't throw direction to the wind, okay? Because why? Because velocity, it didn't say this. What kind of vector is velocity? Or what kind of quantity is velocity? It's a vector quantity. That's right. And what does a vector quantity have? Oh, good grief. How do I spell quantity, y'all? Quantity? If I could spell, I'd be dangerous. Quantity. There we go. Quantity. All right. All right. It's a vector quantity. Huh. Yeah. All right. Okay? And then we see the rest. Negative and increasing, it's getting less negative. What? All right. If it's negative, but it's increasing, that means the positive particles moves it. But if it's negative and decreasing, it's getting, now wait a minute. Negative and decreasing. I think they meant to say right here, if it's negative and increasing, it's getting more negative. That's a boo-boo. Because how can you be negative and increasing? Well, they say getting less negative. Okay, all right, yeah, okay, all right, okay. But why did they say it that way? Okay, getting less negative. Okay, yeah, increasing as far as going up. Yeah, okay, I see what they're saying. Becoming less negative. They explained themselves. Okay, I can live with that. Okay, yeah, all right. And so we're getting more positive direction, then of course getting more negative direction. Okay. Now let me ask you something. Can you have, and I know I haven't got to acceleration yet, but let's just think. Let's just go ahead and think ahead. Think out of the box. Can you have positive velocity but negative acceleration? Absolutely. Yeah. What is, when you get in the car and put the brake on, what is that? It's deceleration, negative acceleration, absolutely. So yeah, so that's another thing that stumps us sometimes is we think, oh, well, if I got positive velocity, I've always got to have positive acceleration. No. If that's the case, you'll never slow down. You hit those brakes and you're going to speed up.
It's based on derivatives. You can have a negative and a next derivative.
Yes, you can. Sure is. Sure is. Very good. Okay. And you know, now on ice, when you hit your brakes, you do accelerate. That's why you don't want to hit your brakes on ice, because of kinetic friction. We'll get to that later. Because you don't want to go into kinetic friction, you want to keep static friction. Because kinetic is a skid. You don't want a skid. You accelerate in a skid. That's why you have anti-lock brakes. I don't know if you knew that. That's why. You don't want a skid. Because of kinetic friction, you actually have an increase in acceleration for a second or two. My God, if you're fixing to hit a semi, you don't want to hit it sooner. You want to stop. You want to stop. All right? You don't want to accelerate. You want to stop. Have you not ever noticed that when you're ice skating? I cannot do that. Can y'all see me on a pair of ice skates? Well, that's a hilarious sight, ain't it? All right, anyway. No. I tried it one time. I went about from here to that table. I said, get me off these things. All right. Up at Gatlinburg. Nope. Not doing it. All right. Same thing with roller skates. Whew, man, that's a, Lord, that's a sight for sore eyes. Now, all right. I just can't do it. But if you'll notice, if you've ever been in a skid or if you've ever been in a car that the brakes did lock, you feel the car kind of feels like it's going to go out from under you there for about a second. Feels like it's because it's accelerating. Okay? All right? And you don't want it to. All right? My old Camaro, man, I had a Rally Sport Camaro, and it would fly. And I would do bandits sometimes. Yeah, drove like a maniac, but anyway, it's a miracle of God I'm alive. But I do bandits. You know what a bandit is, don't you? When you lock the brakes down and slide and turn it sideways or turn it all the way around. I used to do that all the time in my Rally Sport. I'd get up to about 100. Anyway, yeah, I'd freak my friends out. Anyway, yeah, that's crazy. All right. That's about the limit of my wildness behind the steering wheel. But anyway, okay. All right, now, let's look at this position versus time graph. All right, now, I know that's a curve, and it's curved a little bit, but we could take the slope of this straight line and determine the average velocity. Because look, y'all, what is the average velocity equation? Look at it. Okay? Well, x is on the y-axis. So we're saying x2 minus x1 over t2 minus t1. Well, that's the slope equation. Yeah, right? Because look, x is over here on the y-axis. So the slope of that line, now look, you're saying, yeah, but that line is curved. Yes, it is. So that answer would be very general, wouldn't it? It would not be exact. Where would we want to get exact? Right there, and take the derivative or the tangent. Yeah. Yeah. Or we could do what? We could draw a straight line through that point, which that's tangent, and take the slope of that line to find the velocity if we didn't have the function, and find the velocity instantaneously at that point. So there's several different ways to work it. Okay? Now, how are we going to work it? Well, we're not going to work it 5 million different ways. We're going to try to keep it fairly straightforward and simple. But I'm just telling you that just so you know there's more than one way to do this. Because instantaneous velocity, again, we tell you it's the first derivative of displacement, which it is, but there's other ways you can find it too. Okay, all right. If you know the y and the x at that point, then you can find it. Okay, but it's just for that point. All right. All right, and again, that's what we're getting to, instantaneous velocity. Here's another equation. Notice it says as the limit of the time. Here's another one we can stick in. Now, again, do we really need to write this now? No, we know it's the derivative of displacement with respect to time. What is a derivative? It's a rate of change in something. So, notice it says as the time approaches 0. Now, y'all, we're not going to be taking the derivative of 0 time, because typically at time 0, but now sometimes you might not be, but usually at time 0 nothing's going on, but you could be. What does that mean? It just means that as the time approaches a given time interval. 1 second. What's my speed at 1 second? Boom. Not 0.8 or 1.3. 1. All right? Or 1.5. It could be 1.5. It could be 1.22. It could be whatever time you want it to be. Okay? But realize something, that instantaneous velocity is only for that moment. Okay? For that time interval. Everybody with me? So it's a derivative, isn't it? Now look, here again, I just showed you this, didn't it? Find it on a velocity graph. We can calculate it. We can calculate it through the straight line, doing that. We know it's curved. That's legal. But again, that's kind of a paintbrush. It's kind of like taking a paintbrush instead of an artist brush. It's still legitimate. But remember, when you've got a fairly long time interval, you're allowed to do that. You can say average and still be close. Okay. All right. Okay. Any questions? All right. But notice they're showing you this as it gets closer and closer. Now look. Instantaneous, remember what I said, the slope of the tangent. See, I just told you that. So we could do what? Slope of tangent, instantaneous velocity, bam. We could take the slope of that, slope of tangent, boom. We can have instantaneous velocity that way if we don't have a function to take the derivative of. Right? Right. Okay? All right, and do they do that? Is that what they do there? Velocity is, let's see. Yeah, we got a time of what? 4 seconds? Yeah. Yeah. 40 meters per second, yeah. Okay. All right. Do you see how they did that? Notice they chose a broad area. Notice they didn't come in here and say, okay, I'm going to measure it right here. Oh, come on now, you know better than that. Now, this is where old school comes in. Now, old Colonel, I'm going to tell you right now, old Colonel Stamper, we always had to draw this on our graph paper. We had to draw our right triangle for the slope. And y'all, we had to use as much of that graph as we possibly could. And your points, listen, when you collect, did you notice in your graph the other day how all your points on the straight line did not line up perfectly? Okay. When you do it manually with your hands and a ruler, you're supposed to lay that ruler on there and make sure the straight line passes equidistant. You want points equidistant on both sides of the line. It'll pass through a few of the points, but any points that don't pass through, you won't say, for example, if you got a point here, well then you want a point right here that's equidistant from the line. If you got another point right here, then you want another point equidistant. You see what I'm saying? And you might have a couple of points. You might have a point here and a point there that it falls on the line. But you want to put that line right there. Why? Because you're eliminating error. And see, y'all don't know if y'all have ever had to draw graphs manually with your hands and calculate slope that way. That's how we had to do it. And man, I'm going to tell you right now, he told us, he said, you better not come in here and have one like that and do a slope equation, y2 minus y1 over x2 minus x1. He said, I'm going to count off because there's too much error in that. We spread it out because we eliminate error, because we're taking a larger sample of the data collected. Right? That's good scientific knowledge. Don't ever take a slope from 2 points, 2 data sets. Man, you're going to be, because those 2 points might be bad measurements. Or one of them might be. Now you've only got one good set of points. Okay? Does that make sense? Okay?